This will be our unit on uniform circular motion. We have studied linear motion, we've studied projectile motion, and now we're going to go to circular motion. So this is going to bring us to our last study of motion for this year. So what is uniform circular motion? Well, I have a couple questions first that I want to ask you, and those questions are, can an object be accelerating if its speed remains constant? So we're talking about something moving in a circle, and we will say yes. If the direction is changing, therefore it is accelerating because the speed might be constant moving in that circular pattern, but it is still changing direction, so yes, it will be accelerating. So the other question is, can an object be accelerated if its velocity remains constant? No. Velocity is still a vector quantity, and if velocity is constant, speed and direction are constant. So this would be an object that is moving like in a straight line and not in a circular motion. So we are going to focus now on circular motion. So some examples of circular motion on a playground. And if it is spinning at a constant speed, we call it uniform circular motion, meaning that the speed is going to stay the same at any position in that circle. We will not be studying anything that the speed is changing for circular motion. Some other examples. Planets orbiting are revolving on their axis. A disk playing, those would all be circular motion. And then we also have like the moon orbiting the Earth, or it could also be satellites orbiting the Earth. Any of those we would consider to be uniform circular motion. So an object is moving in uniform circular motion will have a constant speed, but does this mean that it has a constant velocity? So we've kind of already addressed this, and we said no. The direction is going to be different at every instant. So if we looked at this example right here, if this object was moving around in the circle, the velocity vector at any point here is going to be tangent to that circle. Okay? So the velocity would be tangent to the circle at that particular point. So those would be our differences in our velocity there, where the velocity is always changing. So if the velocity direction is changing, there must be an acceleration. The acceleration of objects moving in a uniform circular motion is called centripetal acceleration. So it's still an acceleration, but we're going to give it this little subscript C to identify that now we're talking about something that is moving in a circular path. The word centripetal means center seeking, and it is always directed towards the center of a circular path. We have seen several examples where we've talked about something moving in a circle, and we've noticed that this acceleration and the force is always going to be towards the center of the circle. So here would be an example. We have a car moves at a constant speed, so the speed is staying constant around a circular track, although the velocity isn't constant because we know that every different point on that track, the velocity would be changing its direction. So if a car is on a track that is 48.2 meters from the center, they want to know what is the centripetal acceleration. So for our equation, we are going to use acceleration centripetal equals the velocity squared divided by the radius. Okay, we should have seen this where they showed us how the relationship was among these variables. So in other words, all we need to do is take what is the velocity, square that, and divide it by the radius, and make sure that you have like units. And it looks like we do here. If we look at the units on this, you really end up with a meter times a meter over a meter times 1 over a second times a second if I break down this once it's squared. So this is going to cancel out this, and notice my units are a meter per second squared, or we could say a meter per second, and that is that velocity, that is the acceleration units. Okay, so if I did my math for this, it looks like I got about 8.05 meters per second squared. Okay. So that would be the answer for that type of problem. We are also going to relate Newton's second law of motion, which was force net equals mass times acceleration, to circular motion. So if there's an acceleration, a net force must be acting to create that acceleration, and we called that net force a centripetal force, even though that force is supplied by one of our other forces that we are aware of. We call it a force centripetal. So we know this is the second law of motion. We can relate that to circular motion just by using those little subscripts for the circular pattern, the circular force, or the centripetal force, and then the centripetal acceleration, and we can substitute it in there. And for A, as we just did before, it is v squared over r. We can use that to substitute in there. Okay, so since the net force is in the same direction as the acceleration towards the center of the circle, the centripetal force must also always be in the same direction. When we've had this is a vector quantity. Whatever direction that is, the acceleration has to be in the same direction. That was Newton's second law of motion. Whatever direction the force is in, the net force, that would be the same direction that the acceleration is in. So we're going to look at a problem here using that Newton's second law of motion and relating it to circular motion. So this would be an example of the type of problem. We have a car that's moving at a constant speed, and then it's around a 3.25 kilometer track. They want to know what is the magnitude of the centripetal force needed to maintain its motion. Okay, now we need to do a couple things here. If we notice that this is in kilometers and then this is in meters, so we're going to have to convert to like units. Also, this is the circumference right here. So we need to change the circumference into, we need the radius, because we know our force centripetal equals the mass times the acceleration centripetal, which equals force centripetal mass v squared over r. Okay, so we need to have that radius for right here. Okay, so we need to do that conversion in here. So first you got to convert this in your kilometers into meters, and so that would be 3,250 meters equals 2 pi times r. I got for r being about 517.75 meters. Okay, so once I get that, all I need to do is plug in my mass, that's 905 kilograms, times my speed, which was 35 meters per second. Square that. Remember, the square always, that's one thing that people have to make sure that they do. And then divide it by the radius. That was in meters. Okay. When we get this, I got an answer of 2,143 newtons. Okay. Really, our units come out to be a kilogram times meter per second squared, and a kilogram times a meter per second is known as 1 newton. Okay, so that's our unit for force. Now, the force that's applying that would be the force friction towards the center of the circle that's pushing on the car to make it go into the center so that it stays on the road. Another example of a problem, except this time they are asking you for what is the mass of this plane. So we're still going to use the same equation. Force centripetal equals mass times acceleration centripetal, which equals force centripetal. We can say m times v squared over r. So then we can just fill in our variables here. It looks like they want us to solve for mass. So if I want to solve for mass, it looks like I'm going to have to take force centripetal times r, the radius, divided by v squared to get the mass. Okay, just use a little algebra there to manipulate it. And fill in your values and then calculate what is the mass. Now, remember, we've always talked about this force centripetal, and as we talk about it, we got to realize that this force centripetal is not a new force. It is simply a net force that acts in that circular motion. Okay, so that force could be a force applied, it could be a force normal, it could be a tension, or it could be gravitational. So like here with a car moving in a circular, or turning a corner, that's force friction. Swinging something on a string, that's that force tension. Okay, here's just a car saying that centripetal force to require that motion, it's the friction on the wheels that require that, or that give it that ability to follow the circular path. If there isn't enough friction on the road, you would not be able to go in that circular motion. So like when it gets icy and stuff, sometimes you don't have enough friction. So that force centripetal maintains that circular motion. Just like if you tied a string onto a bucket and twirled it in a circle, it's still the centripetal force there, but that force centripetal is being supplied by that rope or string, whatever it may be. So it's really one of our other forces that we have already had before. Okay. Another example, it's the tension in that string or wire. So here we look at the Earth, the Moon system. With this one, what supplies the centripetal force here? Wouldn't it be force gravity? Because this moon is being pulled towards the Earth, although it wants to move in a straight line. So that's what makes it have that circular motion to be able to move in a circular pattern.